Hello everyone, my name is Mohan. I'm from Shanghai Jiao Tong University. The topic of my presentation is malware detection with limited supervised information via contrastive learning on API call sequences. My presentation will include 4 parts: introduction, related work, problem formulation, the model we proposed, and the experiments we made. Let's start with the introduction. I will give the background of our research. Malware is any software designed to cause damage or occupy the resources of the target computer by means of executable code, script. Huge economic losses in the world caused by massive malware pose a considerable challenge for malware detection. Malware detection is the process of discovering and classifying malware based on its characteristics, according to whether the malicious code is executed in the analysis. Malware detection techniques can be divided into static detection and dynamic detection. Static detection extracts the binary code, string, byte sequence, file name from the content of the software code as the signature of the software. The detection can be completed by matching the signatures of the sample with the feature library of malware. Static detection technology is simple and fast, but malware can camouflage itself by means of encryption, encapsulation, and packing to avoid detection. Dynamic detection technology extracts dynamic features for detection by monitoring and recording the running state and behavior of software, which can effectively combat the camouflage of malware. Application programming interface is a typical dynamic feature. If malware wants to achieve its damage goals, it must call some API according to a certain pattern, which is difficult to disguise. Therefore, the malware detection based on API call is more robust and effective. With the development of deep learning technology, many recent work have proposed the end-to-end method that use deep learning models to automatically extract the features from API sequence to detect and classify malware. However, in practice, the number of labeled malware is limited. Labeling malware requires a lot of domain knowledge, and it's expensive to manually construct a large-scale labeled dataset. Therefore, how to make full use of large amounts of unlabeled data for malware detection is an urgent problem to be solved. Second, related work. I will present work that has inspired our research. The dynamic detection methods use feature generated during the software running process, especially the API call sequence. Researchers can find the behavior intent of any software by analyzing its API call sequence patterns. According to the sequence nature of API calls, many methods use sequence learning methods, such as long short-term memory networks, to extract the features from API call sequence. But training sequence learning method usually require a large amount of labels, as the sequence learning method itself cannot make good use of the relationship between unlabeled data. Thus, they may perform poorly when the labels are limited. Graph structured data can reflect the complex relationships between entities, which can not only contribute to unsupervised learning, but also help unlabeled samples obtain supervised information from limited labels. Graph neural network can extract the features from the graph structured data effectively, even when the labels are sparse. The heterogeneous graph brings additional challenges for feature extraction, and many heterogeneous graph neural networks are also proposed to learn their embeddings. Graph neural networks have been successfully applied in many areas, such as medicine research and recommendation systems. There are also many graph neural network-based malware detection methods. The most representative work is G-Droid. Ggdroid maps the software and API into a large heterogeneous graph by building two types of edges based on the invocation relationship and the API usage patterns, converting the malware detection problem into a node classification task. This method all extracts the relationships between the entities by constructing heterogeneous network, but they may ignore the sequential information of the API call sequences. Contrastive learning is a self-supervised learning method that learns the shared consistent features of samples by contrasting their different views. It also has been applied to graph neural network to improve their representation learning ability. One of the most representative work is HECO. HECO is a novel heterogeneous graph neural network with co-contrastive learning. Choose network schema and metapath structure as two views to collaboratively supervise each other. This model gave us a lot of inspiration. Let's briefly formulate the problem. Given a set A as Y, where A denotes the set of Q API, S denotes the set of P software, where a software SI is represented by an API call sequence. Y denotes the set of labels with one type of goodware and C types of malware. The purpose of malware detection with limited supervised information is to classify the software in S when the number of labeled samples is much smaller than the number of the total samples. Next, I will introduce the model we proposed, SCLMD. SCLMD is a new semi-supervised contrastive learning malware detection method based on API call sequence. The overall architecture is shown as Figure 1. In order to make full use of large amount of unlabeled software for training, we first construct a heterogeneous network based on the API call sequence to express the complex relationships between software and API. Since different API may show different importance to software in the graph, a structural view encoder is proposed to learn the structural feature of software on the heterogeneous network. At the same time, in order to utilize the rich sequential properties, a sequential view encoder is designed to extract the sequential features of the software. A semi-supervised contrastive learning framework is proposed to extract the consistent features shared by structural and sequential features. We also propose a hybrid positive selection strategy for contrastive learning to construct the set of the positive pairs. I will introduce these modules separately. First, graph construction. We define a way to construct a heterogeneous graph from API sequence. There are two types of nodes in the graph, namely software nodes and API nodes. If a software calls an API during execution, there exists an edge between these two nodes. The relationships in the heterogeneous graph not only enable all software learn features from each other, but also make unlabeled software obtain supervised information from the limited number of labeled software. Since different API may show different importance, and graph attention network can learn the importance of different neighbors through the attention mechanism to obtain node representation. A get-based structure view encoder is proposed to learn the structure feature of software on the heterogeneous network. Although the structure feature get rich relationship between nodes, they ignore important sequential properties of API sequence. In order to utilize the rich sequential properties, a sequential view encoder is designed based on BIG rule with attention mechanism to extract the sequential feature of the software. BIG rule combines forward and reverse hidden states of GRU to effectively capture the semantic association between the API sequence. The reset gate and update gate in GRU can alleviate the problem of gradient disappearance and explosion with a reasonable computational cost. In order to make the extracted consistent feature better for malware detection, a hybrid positive selection strategy for contrastive learning is proposed to construct the set of positive pairs. It is based on the TF-IDF similarity and the provided limited supervised information. TF-IDF is short for term frequency inverse document frequency. It's a numerical static that is intended to reflect how important a word is to a document in a collection by regarding the software as a document and the API as word. Then the TF-IDF value of each API can measure how important an API is to a software. The higher the similarity of the TF-IDF vectors of two software is, the more similar the two software are in behavior. For each software, we calculate the cosine similarity of the TF-IDF vectors between it and any other software, and select top k ones with the largest cosine similarity to form the k positive pairs with it. In this way, the positive pair set is initially constructed. When some supervised information is provided, the positive pairs set can be further fine-tuned to better guide the feature learning. The fine-tuning is carried out based on the intuition that if two software have the same label, they are positive pairs of each other. While if they have different labels, they are not positive samples of each other and should be removed from the positive set. That's how we got our positive sample pairs. After getting the structural and sequential representation of the software, we feed them into two multi-layer perceptrons separately to map them into the same space where the contrastive loss is calculated. We can calculate the constructive loss with positive pair set. The detailed formulas are in the paper. You can take a look if you are interested. When some label information is provided, the model is trained in a semi-supervised manner. The loss is adopted by combining the contrastive loss with a cross-entropy loss. The structural representation of the software is adopted to perform downstream classification tasks. Because the graph structure helps unsupervised learning and enable the unlabeled samples obtain supervised information from the labeled ones. Then I will show the experiments we made and some conclusions we have got. We employ two real-world malware datasets, ACMD and ICICS. The dataset statistics are in the table 1. ACMD is the Alibaba Cloud malware detection dataset, contains API instructions information from 5,000 benign software and 9,000 malware. There are 7 types of malware, including infected virus, Trojan horse program, mining program, DDoS Trojan, extortion virus. ICICS is a subset of Alibaba Cloud's third annual security algorithm challenge dataset, which contains API instruction information from 5,000 benign software and 5,000 malware, including infectious virus, Trojans, DDoS Trojan, ransomware. We splice the API call during the software execution process into an API sequence according to the time order. The baseline includes 2 sequence learning methods, by LSTM and by group, 2 heterogeneous graph learning methods, RGCN and HGT, 3 specifically designed API call sequence-based methods, MamaDroid, GDroid, and LGMO. MamaDroid extracts the features for malware detection by building a Markov chain-based behavior model from the API call sequences. GDroid maps the software and APIs into a large heterogeneous graph, converting the original problem into a node classification task. LGMO extracts local and global features for malware detection by combining the stacked convolutional neural network and graph convolutional networks. To compare the different methods when different amounts of labels are provided, we randomly select 70%, 20%, 10%, 5%, and 2% of each dataset as training set, and choose 10% as the validation set. The rest of dataset is set as test set. The macro F1 and micro F1 of each method is shown in Table 2. It can be seen that macro F1 is much smaller than the micro F1 on both datasets. This is because both datasets are unbalanced. More than 1/3 of ACMD and half of ACICS is benign samples, and the rest contains the other several classes. Micro F1 can easily get high value on unbalanced dataset when the largest class is classified accurately, even though some small classes are classified poorly. Macro F1 is more strict metric for unbalanced dataset, as macro F1 takes the average value of F1 score of all classes as the result. Thus, macro F1 is more strict and important in our experiments. On both datasets, the macro F1 of SCLMD outperforms those of other methods on all training ratios. The micro F1 of SCLMD is also better than most of the methods, except slightly worse than the MamaDroid and Ggdroid on some cases. This may be because MamaDroid and Ggdroid prefer to classify the software as benign ones, which make them better in micro F1 sometimes, but worse than SCLMD in macro F1 all the time. On both datasets, the performance of all methods decline as long as the training ratio gets smaller. However, the decline degree of the SCLMD is smaller than other methods. This demonstrates that the contrastive learning framework can take full use of the unlabeled data to extract consistent features of structural and sequential view, which help the method work well when the supervised information is limited. To investigate the effect of contrastive learning framework and hybrid positive selection strategy in our method, we designed 3 variants of our model. The first variant only used the structural representation of the software to classify. The second variant only used sequential representation of the software to classify. The third variant, fine-tuning based on labels in hybrid positive selection strategy, is removed. The positive pairs are selected only based on the TF-IDF similarities. The result is shown in the Table 3. It shows that when the supervised information is large, the sequential view encoder can effectively extract the sequential information to achieve better performance. On the other hand, when the supervised information is limited, the structural view encoder achieves better performance as it can use software's rich relationship to help perform unsupervised learning. The result of the third variant shows that the proposed hybrid positive selection strategy can effectively use supervised information in contrastive learning framework. We investigate the sensitivity of 2 parameters, the number of threshold of positive pair k, and the balance coefficient of views lambda. The result with the different k is shown in Figure 2. On both datasets, with the increase of the k, the performance goes up first and then declines for nearly all training ratios. The optimum points of the both datasets are located around 16 to 32. The balance coefficient of views lambda can control the importance of 2 views. The result with different lambda is shown in Figure 3. It is shown that when the training ratio is large, the model with small value of lambda has better performance, because at this time, the sequential view is more important, and the sequential view encoder can benefit from more label information. When the training ratio is small, a larger value of lambda is more favorable, because at this time, the structural view is more important, and the structural view encoder can take advantage of the relationship between samples to achieve better performance with sparse labels. Let me make a conclusion briefly. We propose SCLMD, which is a semi-supervised contrastive learning malware detection method based on API call sequence. SCLMD uses two-view encoders to capture the structure and the sequential features of software's API calling behavior. The two views are mutually supervised to learn the consistent representation of software by means of cross-view contrastive learning. Hybrid positive selection strategy is designed to introduce supervised information in contrastive learning. Extensive experimental results on two datasets verified that the effectiveness of SCLMD, especially when the supervised information is limited. That's all for my presentation. If you have any question, please feel free to contact me. Here is my email address. That's all. Thank you.